Okay, so it's 8:30, I guess. So let's get started right away because we have a lot on our agenda today. So today's topic is going to be linear time properties 2, if you will. We're going to talk about safety properties and liveness properties, which I told you already is kind of a categorization of all linear time properties, as I will show you in this lecture. Before I get started, who of you knows what a linear time property is? Well, that's kind of devastating. So who of you that did not just raise his or her hand did not ask the question, what is a linear time property, yesterday in the exercise class, even though he or she was there? Yeah, so if you don't know, then you have to ask, because it's this lecture will fully build on the last one. So without knowing what a linear time property is going to be very complicated, I think. So just to shortly recap, a linear time property is a set of infinite words, and the alphabet is the set of atomic propositions. So every character is a set of atomic propositions, and they kind of specify what are the allowed behaviors of my transition system. And we say that a transition system satisfies a linear time property if all of its traces are included in the property. Okay, so let's look at invariants again. So invariants, you hopefully recall, are a special kind of linear time properties, namely one that is characterized by a propositional formula. And how does it characterize the invariant? Well, our invariant contains all infinite words. Again, the characters are sets of atomic propositions, such that every set along the way at time point 0, 1, and so on satisfies the propositional logic formula. For example, at every point in time, we do have an A in our labeling, meaning that all the traces at every point, really, they have to have an A. So that's what's called an invariant, and this phi is called the invariant condition of the linear time property. And intuitively, we said safety properties state that nothing bad will ever happen, but we have not talked about this further. We only talked about invariants so far. Of course, invariants are kind of properties that follow this pattern. For example, mutual exclusion says, never is it going to be the case that our two processes are in their critical sections at the same time. Or deadlock freedom saying that never all of the philosophers are in state wait at the same time. Okay, this we already saw, but there are other safety properties I already hinted at that are not as easy. Here these are invariants, you can characterize them by a propositional formula. But this one you can not so easily, right? So for example, the German traffic lights, you could state that every red phase of your traffic light is preceded directly by a yellow phase, for example. Or if you think of the beverage vending machine again, you could state that if the user did not enter a coin, then no drink must be released, right? Or that the total number of coins that the user put in is never less than the total number of released drinks. Okay, so somehow they are different, because these three, they are not invariants, but they are safety properties, but somehow they have to have something in common with the above ones. And what is that? I mean, if we talk about invariants, they are characterized by saying that no bad state will be reached. We showed that an invariant is satisfied if and only if all reachable states satisfy the invariant condition. And these properties, yeah, as I said, it's not so easy there. It's not that there is a particularly bad state, but there needs to be some kind of bad behavior as a combination. But all of them have in common that there is, if you violate the property, then you can already tell after a finite prefix, right? I mean, this is a special case, an invariant of a safety property in general, because yeah, you will see that later actually. But the commonality between all safety properties is that in order to satisfy the property, there must not be a bad prefix of your property present in the transition system, in the traces of the transition system. Okay, let's look at this as an example. So again, take the traffic lights example, where we state as a property that every red phase is preceded by a yellow phase. Well, what would be a bad prefix of that? I mean, a bad prefix of that is obviously, I don't know whether you can see the colors. Is it visible? For me, it's neither. So this is a red, supposed to indicate that the traffic light is red, and this is supposed to be green. Anyway, but you see that if it suffices to look at this finite prefix in order to say that the property cannot be satisfied. So if this finite prefix is somehow in our transition system, or if let's forget about transition systems, but just look at this finite prefix, then we know that no extension of this prefix will ever satisfy the property, right? Because already at this point, because we had green followed by red, meaning that we somehow violated this property, no matter what we put after that, it's going to be violated. Is that intuitively clear? Very good. Okay, and the same thing you can do for the beverage vending machine, where you say that the total number of entered coins should never be less than the total number of released drinks. And if you look at the prefix pay, drink, drink, so 2 drinks were released, but only 1 was paid, then already after that finite part, you can say there is no way that this property is satisfied, right? Okay, and now we're just going to formulate what I intuitively told you formally. Right? And capture safety properties by a formal definition. Okay, let E be a linear time property. So that is, it's a subset of the infinite words over sets of atomic propositions. Then we call E a safety property if the following holds. It looks very technical, but the intuition is very easy. It says that if you take a word, some infinite word that is not contained in the property, it violates your property. It's not allowed by the property. If you take an infinite word, then there must be a finite prefix, so you can cut off this sigma at some position, such that none of the words that start with this prefix ever belong to E, right? So if you have this prefix in an infinite word, there is no way that you can ever extend the word to an infinite word such that it belongs to the property again. And if you restate that, you can write it like this. So E intersected with all the words that have this bad prefix at the beginning should be the empty set. Okay, and this is the characterization of a safety property. So we call a linear time property safety property if and only if we have this property. Okay, and unsurprisingly, these words are called bad prefixes because they tell you, well, after reading this bad prefix, there is no way of ever being in the property. So already at that point, we know that it's violated. And then you could also write down the set E that we started with as the set of all infinite words that do not have a bad prefix. And as some kind of notation that we will use quite a bit in this lecture, we say bad pref of some linear time property is by definition the set of the bad prefixes. So it's exactly those words that you cannot extend to ever get back into your property again. And I want to make that distinction. These are finite words, okay? I mean, it's a major difference. A linear time property, set of infinite words, but the bad prefixes, I mean, it's exactly the point that already after a finite word, you can tell there is no way of satisfying the property. And if the property E is clear from the context, we also use bad pref, but mostly will indicate what linear time property this is referring to. And of course, there may be a lot of bad prefixes, so we also have the notion of minimal bad prefixes, which are all bad prefixes such that no proper prefix of this bad prefix is in itself a bad prefix. So think you have this word A0 to AN. It's a bad prefix, so you cannot possibly extend it to be in the property again. But it could be that you can drop AN in the end and still have a bad prefix. And a minimal bad prefix, this is not possible. So, so you cannot take anything from the back and maintain this property that's a bad prefix. Let's look at an example. So here, can you see the colors here? So the labeling with yellow and red, and these two are labeled with empty set. It's a transition system, supposed to model some kind of traffic light. It can go from yellow to red, red to red and yellow, to green and back. And let's look at the property whether every red phase is preceded by a yellow phase again. Now, if you write this down as a linear time property, it looks something like this. So our property is a set of all infinite words, A0 and so on, over sets of atomic propositions, such that for every position where we have a red in our labeling, we require that it was not the first step, because then it could not have possibly been preceded by yellow. And we require that yellow was actually in the previous set. Okay, I mean, this is the formal statement of this informal property. And if we look at this transition system, we see that it actually satisfies E, because you can only have a red state if it was directly preceded by a yellow state, and you cannot start in a red state. Let's look at this other transition system. It starts in green, so no labels here. This is labeled with red, and this is again labeled with yellow. And here you can already tell that the property is not going to be satisfied, right? But why is that? That you could say it's the case because we have this prefix empty set red, empty set yellow in the finite traces of this transition system, right? Because we can go empty set red, empty set yellow. It's a finite word. It's in the finite traces of the transition system, if you recall the definitions from last lecture. And already after that prefix, we can tell, I mean, it's already violated. No matter how you continue this trace, no matter how you complete it, this infinite word that you'll get out of it will not be in the property. Is that clear? Okay, I see a few nodding heads. But obviously you can say, yeah, why are we only saying that we know at this point? Actually, we know much earlier, right? We know after reading this red here that the property, or that the trace will not be in the property. And this is exactly what a minimal bad prefix is, right? So bad prefix is, for example, this. Also, if you cut off here, is also going to be a bad prefix. But one of the minimal bad prefixes is the prefix empty set followed by red. Because no matter how you extend it, never going to be in the property again. Okay, and you can, for example, then write down the bad prefixes of the property, all bad prefixes, and in this case, it's the set of all finite words, so prefixes, finite words, again over sets of atomic propositions, such that for some position, we actually have the negation of up here, intuitively, right? Because it states that here, that for all positions something holds, and here it says after a finite time, I already have a position where this condition does not hold. So we have red in our labeling, and it was the first time step, which we excluded here, or yellow was not contained in the previous step. Okay. Let's talk about satisfaction of the satisfaction relation for safety properties. Last time, and I already repeated that in the beginning of the lecture, we said a transition system satisfies a linear time property written like this, if and only if the traces of the transition system are fully included, right? So you can think of the property, linear time property E, as the set of allowed behaviors of the system. And what you can show for safety properties is that you can, in order to determine whether this holds, it suffices to look at the finite traces of the transition system and see whether there is any bad prefix of the property in there. And if there is, if the finite trace of the transition system, if there is some bad prefix in there, it tells you then your property is not satisfied. And it tells this theorem also tells you if this is empty, if there is no finite trace that's a bad prefix, then your property holds. And you can take that one step further by looking at the minimal bad prefixes. I mean, this is rather obvious if you already have the statement for the bad prefixes. And if I may take over this projector, I would like to show you exactly this statement. Transition system satisfies a linear time property if and only if the finite traces intersected with the bad prefixes of the property are empty. So let's look at the proof. So please complain if there is something you cannot read. Okay, let's write it down first, what the statement is. So we have a subset of the infinite words over sets of atomic propositions. And in particular, we assume that it's a safety property. Recall what that means from the definition. That means for every word that's not in the property, we can find a finite prefix such that after this finite prefixes, no matter how you extend it, it's not in the property. And we're going to say that T is a transition system without terminal states. Then we have the following statement. T, the transition system, satisfies the safety property if and only if the finite traces of the transition system intersected with the bad prefixes of the property is empty. Okay, so let's prove this. Now we first start with the direction from left to right. So we assume that the transition system satisfies the property, and for the sake of contradiction, we assume that this thing here is non-empty. So the finite traces of the transition system intersected with bad prefixes of the property, it's not empty. Okay, but if it's not empty, then we can take an element from it. So let's do that. So let's have, it's a finite word, sigma head. It's the word A0, A1, and so on up until AN. And it's contained in this intersection. Finite traces of the transition system together with the bad prefixes of E. But what do we know if this word is in the finite traces of the transition system? Well, then we know that there exists a finite path that gives rise to this finite trace. Then there exists pi head S0 to Sn in the finite paths of the transition system, such that the trace of pi head is exactly sigma head. Now, since the transition system, we assume that it has no terminal states, since T has no terminal states. We can also extend this finite path that we took up here to an infinite path, right? Because there must not be any terminal state, so we can always go on. There is pi that starts with S0 to Sn, but then goes on with Sn plus 1 and so on in the paths of the transition system. And if we look at the trace of this path, well, what does it look like? Well, it starts with sigma head, right? So then we have trace of pi is sigma head, and sigma prime, so followed by the labelings of the states Sn plus 1 and so on. For sigma head, sigma prime is L of Sn plus 1 and so on. Okay, but what do we have then? Then we have that sigma is not in the property. Well, why is that? Because sigma head was a bad prefix of the property E, right? Because it was initially taken from the intersection of the finite traces of the transition system and the bad prefixes. So in particular, sigma head is in the bad prefixes of the property. But then, because sigma is an extension of sigma head, we know that sigma cannot be in the property E. And what can we derive from that? Well, we can directly derive that the transition system does not satisfy the property, because we have a path pi as 0, etc., that has this trace, but the trace is not contained in the property. So we directly know it's not, it doesn't satisfy it, and that violates our assumption, so contradiction. Is that more or less clear? And can you actually read that, or is it too small, or no complaints? That's good. Maybe because it's early in the morning, but let's look at the other direction. For the other direction, we have to show that if the finite traces of the transition system T and the bad prefixes of the property intersected with that is actually empty, then the transition system satisfies the linear time property. And for the sake of contradiction, again, we're going to assume that this is not the case. Okay. So, but if the transition system does not satisfy the linear time property, that means there is a trace in the transition system that's not contained in E. That's the very definition of the satisfaction relation. So we have that for some path pi, the trace sigma, its trace sigma is not contained in the linear time property. Then we know still that E is a safety property, as E is a safety property. And we have that the sigma is not, it's not in the linear time property. By definition, there exists a finite prefix, again, that I cannot extend to be in the property again. So for all sigma prime, it is sigma head, sigma prime, not contained in the property E. I mean, that's just applying the definition, really. So we started with, we have a trace that's not in the linear time property, but when it's not in the safety property, then we have a finite prefix that we cannot extend to make it back into the property again. So for all extensions of this prefix, we have that it's not in the property. But then the sigma head is in the finite traces of the transition system, because we have some path that gives rise to sigma, well then a prefix of this path is also giving rise to this prefix of the word sigma. And we stated that earlier, that sigma head is a bad prefix of the property. Well, but that's a contradiction to the fact that we said there is no element that is in the finite traces of the transition system and is a bad prefix at the same time. But we just showed that under this assumption that T does not satisfy the property, then there is such a common element. Okay. Let's move on. So, is it true that every invariant is a safety property? Well, I already told you that. Yes, it is. But why is that? Okay, it's first of all, let's assume that E is an invariant with condition phi. Yeah, well, it's very easy to characterize the bad prefixes of this property, because we said that if at some point during a finite word I already have violation of my invariant condition, then I cannot possibly extend it to satisfy the property again. Well, and if I can define a set of bad prefixes that characterize my property, well, then it's by definition a safety property. And the minimal bad prefixes are such that the first n-1 elements all satisfy the property, the invariant condition, and the last one does not, right? Because then after, you cannot take away the last element, this an, because this actually explains violation of the invariant, which is why this is the set of minimal bad prefixes. Is the empty set a safety property? Well, yes, because it's even an invariant, right? Actually, all finite words are bad prefixes, right? Because after having read the first item, you can already say that the result, you cannot complete this trace to ever be in your property again. And the invariant condition for this invariant empty set is the condition false. So there is a propositional formula such that that characterizes this linear time property. So it's an invariant. Is the set of all words a safety property? Well, yes, it is. And why is that trivially the case? Because remember the definition of safety properties. It stated something about, for all words that are not contained in my property, I have something. But if all words are in your property, then there is nothing to require. So by definition, this is trivially a safety property. Let's come to the prefix closure. This is going to be an important notion in this lecture. If you have an infinite word, sigma, then we define pref of sigma to be all finite prefixes. So you take that infinite word and you chop it off at some point in time. Then you obtain a finite word, and all those finite words are contained in pref of sigma. Then you lift this by saying we don't only look at the prefixes of infinite words, but let's look at a set of infinite words and define pref of this set, of this linear time property, if you will, as the union of all prefixes of the contained words. So you take your set of infinite words E, take every individual word, chop it off at every point in time, and obtain all the prefixes allowed by the property. So pref of E says what are the prefixes that are allowed by the property. And now this definition, so for me it always takes some time to process this, but this defines the prefix closure of a linear time property. So we have a linear time property, set of infinite words, and we say the closure of this set of infinite words is again a set of infinite words. But what kind of words are contained in there? Well, it's exactly those words such that all prefixes are also prefixes of the whole property E. So for me, it always takes some time to think about this. So if a word is in here, it means that when you cut it off at some point, right, then you obtain a finite prefix. And you can definitely find that prefix as a prefix of some word in the property. That's what it says. Right? And if this is true for all the prefixes of the word, then it's contained in the closure. And first of all, it's, if you think about it, it's rather clear that the closure only adds new words. Right? So it kind of extends the linear time property E, because, I mean, the prefixes of a word are contained in the prefixes of the word itself. And since we said that pref of E is the union over all words, this clearly contains all the words in E, but it may contain more. And we're going to see this in the course of this lecture. Okay, but this is the prefix closure of a linear time property E. And given all these definitions, this is just a repetition from the previous slide. Given the definition of the closure of the linear time property as all infinite words whose prefixes are fully contained in the prefixes of the property, we can state the following theorem that we're also going to prove. It characterizes safety properties in the sense that we can say E is a safety property, a linear time property is a safety property if and only if its closure is the property itself. Meaning that E is already closed, you could say. So even after applying the closure operation, you don't add any new words. It's exactly then is it a safety property. And yes, we're going to prove that now. Oh, and by the way, if you have any questions, right, just ask right away. Okay, so what's our statement? Our statement, is E is a safety property if and only if the closure of the property is the property itself. So the closure operator didn't add any new words. Let's look at the proof. Well, actually, we make a case distinction to make our life easier. The first one, we say, what about the specific property containing all words? As we've seen, this is a safety property because it trivially satisfies the definition. So we also have to look out for that. So this is our first case. But then by the definition of E, we also have that the closure of the set of all words, as I said, the closure is only adding infinite words to the property, so to speak. And because we already have all infinite words, well, then the closure of the property is going to be the property itself. And we saw that E is a safety property. And then we're done here for this case. So we got rid of that, but we have to talk about all other properties still. So let's look at the case where E is not the set of all infinite words over to the AP. Now, we still have to show both directions, right? I mean, we restricted E to a specific case, but we still have to show both directions. And let's start with the one from right to left. So we assume this. We want to say that if the closure is the property itself, then E is also a safety property. So we assume closure of E is E itself. And that's an infinite word, sigma in the complement of E, meaning 2 to the AP omega without the set E. And this is why we made the case distinction this here. It's non-empty because the set E is not the set of all infinite words. Okay, so we assume that the closure of E is E itself, and we just take one word of the complement, and there must be such a word in the complement because we're not talking about the set of all words to begin with. Okay. Then we have that sigma, this infinite word, is not in E, right? I mean, we took it from the complement of E. It's not contained in E. And because we know that the closure of E is E itself, then it can also not be in the closure. Thus, there exists a finite prefix of this infinite word sigma. Let's call it sigma head, such that sigma head is not a prefix of the property E. Well, why is that? Our definition of closure of a linear time property, we add all the words such that all prefixes are prefixes of the property. But we just said we have a word, sigma, that is not in the closure. So there must be some prefix that we cannot find as a prefix over in the closure set, okay? Then, by definition of the closure, there is no sigma head, sigma prime contained in E. Right? Because this says sigma head is not in the prefixes of E, meaning there is really no word in E that has sigma head as a prefix. Meaning that no matter how you extend it, it's not going to be in the property. But this is exactly our characterization of a safety property, recall? And therefore, E is a safety property. Right? Because we took an arbitrary element, sigma, that is not in the property, and we showed that no matter how you extend it, there is no element sigma head, sigma prime in E, and this was the very characterization of a safety property. Okay, so much for that direction. Let's move to the other direction. Now for the other direction, can you read it? We have to show that if E is a safety property, then the closure of the property is the property itself. And to show this, typically you show that E is contained in the closure of E and the closure of E is contained in E, right, to get equality. But I already said that, and it's rather easy to show, so I'm going to omit that here, the direction that E is contained in the closure of E. Because as I said, the closure only adds new words. E is always contained in closure of E. So we have this part trivially. So it remains to show that closure of E is a subset of E if E is a safety property. Okay, so how are we doing that? We assume that the contrary to show a contradiction. So let's say the closure of E is not contained in the set E itself. Sorry. Well, then we can take an element that is in the closure but not in E. Right? So we take sigma, A, 0, and so on. That is in the closure of the property without the property itself. I mean, this is our assumption, and we're going to show that this is going to produce a contradiction. Then E is still a safety property. And by this assumption here that we made, we have that sigma is not contained in the property, right? Because it's in the closure, but not in the property. But E is the safety property, so there must exist, by definition, a finite prefix such that no continuation of that prefix is in E again. So let's write that down. Then there exists a finite prefix sigma head, A0 up until some point an of sigma, such that sigma head is a bad prefix. I mean, that's saying nothing else than you cannot continue it in any way to get it back into the property. Okay. Now then we have that sigma head is in the prefixes of sigma, right? Because we said sigma head is a prefix of sigma, so that's very trivial. And we have that the prefixes of sigma are fully contained in the prefixes of E. Why? Well, because sigma is in the closure, right? And the definition of closure says it's exactly those words that satisfy this here. It's those infinite words whose prefixes are fully contained in the prefixes of E. So we have this one here. And because of these two things, I mean, you see sigma head is in the prefixes of sigma, and the prefixes of sigma are fully contained in E. We already know that sigma head is in the prefixes, must be in the prefixes of E. But if it's in the prefixes, what does that mean? It means there is an infinite word in there such that sigma head is the prefix of this infinite word. And there is a sigma prime such that sigma head continued with sigma prime is in the property E. Otherwise, sigma head would not be a prefix of E. But this is a contradiction to the fact that sigma head is a bad prefix of the property. Right? We just showed that we found a continuation of sigma head that is in the property, but above here we showed that sigma head is also a bad prefix, meaning no continuation is in the property. So this clearly is a contradiction. So we're done here. Is that more or less clear? So, I mean, it definitely, I think, takes some time to get used to this prefix closure, to all these notations. But I hope you at least get an idea about this. Okay, so let's move on. There's plenty that we have ahead of us. Now recall from the last lecture that if the traces, so if we have two transition systems, T1 and T2, and the traces of the first one are fully contained in the traces of the second one, then this is equivalent to having that for all LT properties E, if the second one, T2, satisfies the linear time property, then also the first one satisfies the property. I mean, this we already had in the last lecture. And what you can actually show is the following if we look at safety properties only. If we have two transition systems, T1 and T2, that are not connected by trace inclusion but by finite trace inclusion, meaning that all finite traces of T1 are contained in the finite traces of T2, this is equivalent to having that for all safety properties E, if the second one satisfies E, then also the first one. Right? So it's very similar. It's just that here you have infinite trace inclusion, here you have finite trace inclusion, here you say all LT property, for all LT properties you have a statement, and here you say for all safety properties. So for a subset of the linear time properties you have this. Yes, this is the statement we just had. So let's quickly go through the proof, but it's rather straightforward, I would say, especially the direction from left to right. So suppose we have that the finite traces of T1 is fully included in the finite traces of T2. And recall that we just showed that a transition system satisfies a safety property if and only if the finite traces intersected with the bad prefixes of the property is the empty set. Okay, so how are we going to show that if we have finite trace inclusion, then for all LT properties we have the implication that if T2 satisfies the property, then also does T1? How are we going to do this? Well, we know that T2 satisfies, so let's take an arbitrary safety property, and we know that T2 satisfies it. I mean, that's the part on the left-hand side of the implication. But then we know that the finite traces of T2 do not contain any bad prefix, right? So the finite traces of T2 intersected with the bad prefixes is the empty set. But since the finite traces of T1 are included in the finite traces of T2, we know that the finite trace of T1 intersected with the bad prefixes is a subset of this one. And if this one, the finite traces of T2 that are bad prefixes, is already the empty set, where then clearly also the same holds for T1. And we have that T1 satisfies the linear time property, the safety property E. Now the other direction is a bit more involved, but not too much. So let's quickly go through it. So we have to show that if we have that for all safety properties E, we have the following, then the finite traces of T1 are included in the finite traces of T2. Let's pick as a linear time property this one, so the closure of the traces of T2. And in order to apply this on the right, what we have on the right-hand side here is we have to first show that it's a safety property, right? Because this, I mean, we can look at it, but it's not directly obvious that it's a safety property. But in order to actually use this, we need that it's a safety property. Now again, here, quick reminder that the closure of some set, and in this of some set of infinite words, in this case the traces of T2, are all words such that the prefixes are fully contained in the prefixes of this one. And here we already substituted that with the finite traces of T2, because you can show that for each transition system you have that the prefixes of the traces of the transition system are exactly the finite traces of the transition system. And this is not hard to see. I mean, we don't use that here in this proof, I guess, but anyway, it's a nice thing to know. So why is this a safety property? So, I mean, in order to show this thing implies this thing, we have to somehow make sure that we can apply it. So it must be a safety property. Why is it a safety property? Well, it's a safety property because you can show that the closure is an idempotent operation. So if you apply the closure to some set of infinite words, and you apply the closure again, it's going to be the same thing. So no matter how often you apply the closure, it will stay at the same. It will stay the same. And this is exactly the characterization we had for safety properties. Remember, so we have that closure of traces of T2 is closure of traces of T2, and therefore E is a safety property. And then we can use this one. So then we may assume, because we showed that E is a safety property, then by assumption T2 satisfies the property E, and now we have to show, so we can assume that T1 also satisfies the property, and from this we need to derive that the finite traces of T1 are included in the finite traces of T2. Well, what does it mean that T1 satisfies the linear time property E? It means that all of its traces are fully contained in the linear time property. That's just the definition of it. And given all these tiny fragments here, we can now basically create a chain of reasoning that shows that the finite traces of T1 are included in the finite traces of T2, and it goes like this. The finite traces of T1 is the set of prefixes of the traces of T1. Remember, we had this like three overlays ago. This holds for any transition system. So if you take the traces and you take the prefixes of that, you arrive at the finite traces of the transition system. Now, because T1 satisfies the linear time property, we know all its traces are included in E. So by taking the prefixes of a larger set, so we make this one larger by moving to E, we also have more prefixes, which is why we have this subset relation. Then putting in the definition of E means that this is the prefixes of E are the prefixes of closure of traces of T2. And then you can show that this is the same as the prefixes of the traces of T2. So you can essentially drop that closure. Why is that? Intuitively, it is because the closure operation does not introduce new prefixes. It may introduce new words, infinite words, but no new prefixes. So you can cross out the closure here, essentially, and then you are stuck with the prefixes of the traces of T2, and just like here, we then know this is exactly the finite traces of T2. I know this is a bit quick, but I think you need to take your time at home and maybe think about it once more. So safety and finite trace equivalence. So remember, we just showed that the finite traces of so that finite trace inclusion is the same as having that for all safety properties, if T2 satisfies the safety property, then so does T1. And obviously, just like for trace inclusion, you can lift that to trace equivalence and finite trace equivalence in this case. So you have that if you not only have inclusion, but you have inclusion in both directions, so the finite traces of the two transition systems are the same, then the T1 and T2 are not distinguishable by safety properties. Okay? Are there any major questions up to that point? No. Okay, just a summary, right? We have seen all these before, but summary. If we have trace inclusion, then we have that for all LT properties. If the transition system that has more traces satisfies the property, then so does the one with fewer traces. We have the same thing for finite trace inclusion. If we have finite trace inclusion, it's the same thing as saying that for all safety properties, we have that if the transition system with more finite traces satisfies the property, then so does the one with fewer of the finite traces. And the same thing for trace and finite trace equivalence. Right? I'm not going to go through all of that, but it should hopefully make sense to you by now. Let's have a short quiz again. So if we have that the traces of some transition system are included in the traces of the transition system in some other transition system, is it the case that then also the finite traces of one of the first one is included in the finite traces of the second one? What would you intuitively say without actually justifying it? Yes. You would say yes, and this is good because it's correct. Because, I mean, on the previous slide I already mentioned that the finite traces of a transition system are the prefixes of the traces of the transition system, and then it's clear because if you have a larger set, so a superset, then you also have more prefixes, and then you also have finite trace inclusion directly. Okay, so we just said if we have trace inclusion, we have finite trace inclusion. What about the other way around? So if we have finite trace inclusion, do we also have trace inclusion? What would you intuitively say? No guesses? Yes? One guess?
I would say no, because when we only look at finite prefixes and they are the same,
Yes?
then that says nothing about infinite words. And there the sets could differ.
Yes and no. You are correct, first of all. It doesn't hold. But the argument, I mean, if you have finite trace inclusion, it means, you're right, it talks about finite prefixes, but of arbitrary length. So it somehow means you can copy it arbitrarily deep. And as we will see, under certain assumptions, it holds again, but in the general case, it doesn't. So the answer is no. And let's look at an example. So here we have a transition system T, very tiny, so just a state with a self loop, labeled with empty set this state. And here, it's a very large transition system. It's infinitely large. So we have an initial state here, and then we have an infinite branching from this initial state. And you already see the pattern. It can enter like a chain of having empty set, empty set, empty set, and at some point it will always go into a state labeled with B, and from there on only see B forever. And yeah, let's look at the traces and finite traces of these two transition systems. So it's clear that for this transition system, the only trace is empty set infinitely often, right? Because you start there and you stay there. You just read off the labeling, it will just be the empty set forever. Now the finite traces of this transition system is equal to an arbitrary but finite amount of empty sets. Can someone tell me why this is wrong? It's very easy, but okay, so to my opinion, that should be a 1, right? Because if you have n0, it means you have nothing, right? And our traces, also our finite words, they always contain at least one letter, okay? So think of that being a 1, okay? But other than that, it's correct. Let's look at the traces of this other transition system, T prime. The traces, they have an arbitrary number of empty sets that is greater than 2, but other than that, you can have, depending on which branch you enter, you will have an arbitrary amount of empty sets, followed by B forever. But then if you look at the finite traces of this transition system over here, you see that it also contains, again, think of that being a 1, an arbitrary number of empty sets, right? Because if I, go down the 100th branch or so, then I can make 100 steps of seeing an empty set. And if I want to see more empty sets, I just go down further to the right, and so on. So in this thing, we have that it's possible to obtain the finite traces that have an arbitrary number of empty sets. But of course, you can also have an arbitrary number of empty sets, if it's at least 2, and followed by an arbitrary number of Bs. But the important point is that it's also possible to stop the finite trace before reaching the Bs. Okay? And then you already see that the finite traces of T, they are included in the finite traces of T prime, right? Because this set, being a 1, is directly a subset of this one. But at the same time, we have that the traces of this transition system, so empty set forever, is not an element of the traces of this other transition system, because eventually you will end up in a B in the transition system on the right-hand side. I mean, you could say it's an artificial example because you have infinite branching and so on, and indeed it is. And indeed, under certain restrictions, as we'll see, it actually holds. The statement that finite trace inclusion implies trace inclusion. Okay, so we just saw that in general this doesn't hold, and the result saying that if we have trace inclusion if and only if it's not distinguishable by LT properties, it means that because we don't have trace inclusion, there is a linear time property that distinguishes the two. And what property is it? Well, for example, eventually B. You have that this transition system satisfies eventually B, right? Because all traces will eventually reach a point where you have B in the labeling, whereas this clearly doesn't. Okay? But under certain restrictions, I already hinted at, it actually holds. So what are those restrictions? So one possibility to do that is to require that the first one, the T, has no terminal states, meaning that all paths in the transition system T are infinite. And we require that the second one, this T prime, is finite. So that might look somehow artificial to you as well, but if you look into the proof, it actually makes quite a bit of sense to require these things. And then you can show, under these assumptions, then trace equivalent or trace inclusion is the same thing as finite trace inclusion. And I mean, we already saw that the implication from trace inclusion to finite trace inclusion, this holds for all transition systems, no matter whether you have this or not. But if you additionally have these two things, then also the other way around, finite trace inclusion means trace inclusion. Here I'm quickly going through this because on the slides there is some kind of a proof idea. And I would somehow like to show that to you, but I'm afraid this takes more time than I have. If you want to see this, if you're interested in this proof, please send me a mail, and depending on how many people are interested in that, I will maybe have a short Q&A session in our office, or maybe cut some time off the exercise class to show the proof idea. Because I really like it, it's really a neat idea. But it's not essential to the contents of this lecture, so I'm going to omit that here. Okay, so now suppose we have shown this. Suppose that under these assumptions we have that finite trace inclusion implies trace inclusion. And what you can show is that these are not the only restrictions that you can make for this result to hold. But you can somehow weaken this. Here we said T prime is finite, is maybe not something you want to have, but you can show that image finiteness is actually sufficient. And image finiteness, what does that mean? It's very much related to the notion of AP determinism that we had in the exercise class. Image finiteness means that if you are standing on a specific state, and if you look at the successor states of this one state, then there are only finitely many successors that are labeled the same. So, there may be infinitely many successors that I have standing on the current state, but if I take a specific set of atomic propositions, then only finitely many of them will be labeled the same. So if I take, for example, the atomic propositions A, B, C, only finitely many of them will be labeled with A. Only finitely many of them will be labeled with A and B, and so on. Of course, if you have finitely many atomic propositions, then image finiteness directly implies finiteness. But if you have infinitely many atomic propositions, then image finiteness is strictly weaker. And of course, you not only require this for the successor states of all the states, but also for the initial states. So for every set of atomic propositions, there are only finitely many initial states that are labeled with exactly this set. Okay, but the bottom line is that under certain restrictions, you can show that finite trace inclusion implies trace inclusion. That's what you should take away, probably. Okay, so let's lift this to trace equivalence, moving from inclusion to equivalence. So if we have the traces, that the traces of two transition systems are the same, then clearly we also have that the finite traces of these transition systems are the same. This follows the result we had previously for trace inclusion. But again, the reverse direction does not hold in general, and even not for finite transition systems. So let's look at an example. Two very finite transition systems. And if you look at them, then the traces are the same. The finite traces are the same, but the traces are not. Right? So here you have this trace that goes down there, but here, if you try to mimic that trace in the left-hand side, you need to continue from there. So there is no point, you cannot stop here, because it's not a terminal state, whereas here it is. So the traces of the transition system are different. But again, under additional restrictions, for example, that both of them are finite and do not have terminal states, or both of them are AP deterministic, you can show that finite trace equivalence implies trace equivalence as well. Okay, I hope I have not shocked you too much. I know we realize that this is one of the lectures that are very proof heavy and a lot of notation and so on. But I think if you look at it again, you will hopefully be able to handle it. So let's move on. We talked about safety properties now. Safety properties, that were the properties that set of infinite words, such that if I have a word that does not belong to my safety property, I can always find a finite prefix that I cannot extend such that it belongs to the property again. And now the dual to this is called liveness. Liveness. Intuitively, it states something good will eventually happen. What might be examples for this? For example, an event A will occur eventually. For example, my program will terminate at some point. I don't know when, maybe after 5 steps, 100 steps, I don't know. But eventually, at some point. Or something will occur infinitely many times. So the dining philosophers infinitely often eat, or something like this. Starvation freedom. Or whenever some event B occurs, then at some point in the future A occurs. Like with the critical section, we had an example where we said, if we at some point are waiting for to enter the critical section, then we will do so. These are examples for liveness properties. And can you tell me, why are they not safety properties? I mean, they seem to be somehow different from what we had until now. Why are they different?
Even if some prefix is satisfying them, they can still be extended by something that violates them later.
But yes and no. I would formulate it, dually, but I would say that give me a finite prefix, you can choose it. No matter which finite prefix you give me, I can extend it such that it is in the property, right? So think about termination. So you give me a run of your program that ends somewhere, but then I can complete it, right? So that it eventually terminates. Of course, I cannot do that for all the programs, but with respect to the property, I can, right? You cannot give me a finite prefix that I cannot complete somehow to be in my property again. I can always choose a suffix such that the whole infinite word will be in my property again. And that's exactly the difference between safety properties and liveness properties. So let's have a quick quiz. So a few properties, and I want you to determine, are these safety properties, liveness properties? Neither of them. As we can see, there are properties that are neither liveness nor safety properties. Let's talk about it. Each philosopher thinks infinitely often. Liveness or safety? Yes, one? Liveness, right? Because if you give me a finite prefix, no matter what happens there, I can complete it such that each philosopher thinks infinitely often. Even if no philosopher has thought so far, right, I can still complete it in a satisfactory way. So this is a liveness property. Two philosophers next to each other never eat at the same time. It's safety and it's even an invariant, right? Because it means that at every point in time you have a specific condition, but in particular every invariant is a safety property, so yes. Whenever a philosopher eats, then he has been thinking at some time before. That's a bit harder, I agree, but still a safety property, right? Because if you give me a finite prefix where some philosopher is thinking without having, if he's eating and has not thought before, then I cannot complete it to be back in the property, right? Whenever a philosopher eats, then he will think sometime later. Yes, I heard some. It's liveness, right? Because no matter which finite prefix you give me, I can extend it by just extending it with some think after. If some of them have eaten before, I can extend it with some things so that we are back in our property. Yeah, sorry. With some of think atomic proposition inclusions. That should be the way to phrase it. Okay, and then finally one property: between two eating phases of philosopher I lies at least one eating phase of some other philosopher I plus 1. Yes? I would say it's safety. So first of all, because how can you violate this? Well, if you think about violation of this property, it means that philosopher I ate 2 times without having philosopher I plus 1 eat in between, right? But if you then give me this prefix that contains this behavior, there's nothing I can do. I cannot extend it to be contained in the property again, right? So safety. Okay. Now, there have been several notions of liveness defined in the literature. Here is just one of them, but in our context, this is very fitting because it's pretty much the dual of our definition of a safety property. Okay, and the formal definition says just says what we intuitively said. We said an LT property, linear time property, set of infinite words over sets of atomic propositions. It's called a liveness property if every finite word can be extended to an infinite word in the property. Right? It's exactly the dual what we had to safety properties. And if you formulate it differently, it means that the prefixes of the property, the prefixes of all the words contained in the property, are all finite words. Right? So for every finite word, I can find a word in my property that starts with this finite prefix. Because we said I can complete every finite word such that it is contained in the property. That's exactly the definition. Okay, let's not go through all of these examples again. I mean, they are essentially what we had on the previous slide. Let's maybe look at this example, formulate an LT property that is a liveness property. So say we have n processes, and we have atomic propositions, crit I, for all these n processes, crit 1, crit 2, and so on. And we want to state that each process will eventually enter its critical section. Well, then we can define this as a linear time property, set of infinite words, of the form A0, A1, and so on, such that for all processes, there exists a point in time where process I is in its critical section. Right? Yeah, this is all very unsurprising. You can also extend that you will enter the critical section infinitely often. Yes, as I'm running out of time, I will move through this quickly, but I hope you get the idea already. And now we will show an important connection or an important result about safety properties and liveness properties and how they relate to each other and how they categorize the set of linear time properties in total. So recall, it looks very technical, but it's just what we had in the first part of the lecture. It says, what is a safety property? A safety property is a set of infinite words such that for all elements that are not in the property, there is a finite prefix such that no matter how you extend that prefix, you will not be in the property again. And we showed by a formal proof that E is a safety property if and only if the closure of E is E itself. So E is already closed under the prefix closure. And just for repetition here, a reminder, the closure of a linear time property E is a set of all words whose prefixes are the prefixes of the whole set, are contained in the prefixes of the linear time property. Let's come to this main result about safety and liveness. I mean, I already hinted at the fact that there are, in fact, linear time properties that are neither a safety property nor a liveness property. So are we supposed to look at some new class of properties or what? And the fact is, no, we do not have to do that because of the following result. You give me an LT property, E, arbitrary one, set of infinite words over sets of atomic propositions. And I will give you two properties back. One, a safety property and a liveness property. And they will be chosen in such a way that your property is the conjunction, or if you will, intersection of the two properties I'm giving you back. So what does it say? It says every linear time property can be decomposed into a safety property and a liveness property in the sense of intersection of those two properties, again, give you the original linear time property. So in some sense, you can say safety and liveness are everything you need. So let's prove it. How do we prove it? Let's start. So given some linear time property E, we have to say what is safe and what is live such that these conditions are satisfied. And we take safe to be the closure of E. Well, why not do that? This is just a reminder of the formal definitions. And we choose live, the property live, to be E joined together with the complement of the closure. Okay, we can do that. But obviously, we still have to show that if you define safe and live to be like this, then, first of all, the intersection of the two is again the property E. That's one thing. we need to show that safe is a safety property, and we need to show that live, as defined here, is a liveness property. And we're now going to do that. So I would argue it's more or less obvious that the intersection of them is E again. So if you take closure of E intersected, so these two intersected, closure of E intersected with E union of the complement of the closure, well, if you resolve that, then what remains is just E. That's rather straightforward, so let's not do it here. Would also argue that it's rather easy to argue why safe is a safety property. Do you have any intuition as to why that might be? We already had a similar case on some slide before. Yes?
Because it's already a closure.
Exactly, because it is already a closure, and I told you that the closure is an idempotent operation. So if you have some set of infinite words, take the closure, then you possibly extended it, but if you then take the closure over and over again, you will not add more words. So we have the closure of safe, because it is already a closure of some property E, is again the property itself. And remember, we showed this theorem that if we have this for a property safe, then safe is a safety property. So the only thing that remains is that live is a liveness property. And this is actually what we're going to show now as the final proof of today's lecture. And for this, we need to show that all finite words are prefixes of the liveness property. And this is not that difficult, actually. So oops, sorry. Proof. So we assume the contrary, that the prefixes of this property live are not all finite words. Well, then we can take a finite word sigma head that is in, so it's a finite word, 2 to the AP plus, that is not a prefix of live. Right? Because we said, okay, we have a prefix, so if we have a finite word that's not a prefix of our liveness property, well, then we can take it. But then there is no sigma head, sigma prime in live. Why is that? Why is no continuation of sigma head in live? Yeah, because if it were, then sigma head would be a prefix of live, right? If there was some infinite word in live such that sigma head is a prefix of it, sigma head would be contained in this set, but by our assumption it's not. Therefore, there is no sigma head, sigma prime in E joined with the complement of the closure of E. That is just plugging in the definition of live here, right? So I substituted live with our definition that we gave for the liveness property. But what does that mean? If we don't have a word of the form sigma head, sigma prime in the union of these, it means in particular that we have no such word in E and that we have no such word in the complement of the closure. This implies that there is A, no sigma head, sigma prime in E, and there is point B, no sigma hat sigma prime in the complement of the closure of E. Okay, so we have sigma hat sigma prime. So we have no sigma hat sigma prime in the property E. But then we directly get from that that sigma hat is not a prefix of the linear time property E, right? Because it can only be a prefix if there is some word, some continuation in the property, but there is none. So we know that sigma hat is not a prefix of the property E. And from B, we get that there exists sigma hat sigma prime in the closure of E. Well, if we said there is no continuation of sigma hat that is in the complement of the closure, it means all continuations of sigma hat are in the closure, so we can in particular take one. But then by definition of the closure, this implies that sigma hat is a prefix of the property, right? Because we have something that is in the closure were exactly those words such that all of their prefixes are contained in the prefix of the property. And we derived that sigma hat is not a prefix of E, and we derived sigma hat is a prefix of E. So we have a contradiction. And which means that our assumption cannot have been correct. And we know that the prefixes of our liveness property are all finite words. Okay, we will be done right on time because there is only one slide missing that I will show you. So we have just seen every linear time property can be decomposed into a conjunction of a safety and a liveness property. But are there properties that are both liveness and safety? What would you say? I see a shaking head here. Okay. As it turns out, yes, there is. Sorry, but it's just one. It's really just one, and it's a set of all words. It's the only property, the only linear time property that is both safe and live. Well, first of all, what we can easily verify is that it's a safety and a liveness property. I mean, we have already seen it in some earlier proof that it's a safety property, but it's also a liveness property because, if you take the prefixes of all words, it means that you will also get all finite. If you take the prefixes of all infinite words, you will get all finite words, which is exactly the definition of a liveness property. So it's easy to verify that it is actually indeed safe and live. But you could argue, is it the only one? How do I know? Well, let's check. So we just proved that, from the definition of a linear time property, we know that it's a liveness property. If it's a liveness property, then we have that the prefixes of the property are all finite words. I mean, that's just applying the definition. But then if you apply the closure, then you know that the closure of this property E must be the set of all infinite words, right? Because the closure, it doesn't introduce new prefixes, but it adds all infinite words whose prefixes are fully contained in this set. And this set is the set of all finite words, so the closure of E will be all infinite words. And since for a safety property we have that the closure and the property E must be the very same thing, it directly follows that the only linear time property that can satisfy both the definition of a liveness property and a safety property is in fact the set of all words. And yeah, thank you for your attention and see you on Friday probably.